Differential equations. That's what this course is all about. But as the name suggests, differential equations require the knowledge of derivatives. That is a prerequisite for this course. This video is not meant to be a complete course on derivatives. If you haven't encountered derivatives before, that is not a video for you. It is just a recap of the most fundamental concepts when it comes to derivatives, so that you would be confident in your abilities before you try to tackle differential equations. So, if you haven't dealt with derivatives before, I suggest that you find some other source to learn about these. But if you have some exposure to derivatives, this is a video for you. So, what is a derivative? Well, we might define this as an instantaneous rate of change of some function. If we have some function f of x, let's say this one in white, what we might do is we might pick a point, draw a tangent to it, and then the slope of that tangent is going to be our derivative, our rate of change. Now, the way we can define this algebraically is using the following expression. So this is the usual notation, where we have d over dx, meaning the derivative with respect to x, and then of, next to it, we have the function f of x. Now, we can define this to be the following limit. And the intuition behind this is that you essentially pick 2 points and you try to make them very close together. You essentially divide the difference in y between them by the difference in x between them. And as you make this h, this difference in x between them, as small as possible, you will essentially start approximating the tangent line and specifically its slope. Now, how do we deal with this in practice? Let's have a look at an example. F of x is equal to x squared. Now, to find the derivative of this function, we plug in this function into our expression. So we have d over dx of x squared, and we plug that into the right-hand side of the previous equation. So here, essentially, we have to make h, we have to see what happens when h approaches 0. Now, we can't just do that yet because we have h both in the numerator and denominator, and only some of the terms in the numerator have the h. So we might as well expand x plus h squared. When we do that, we might notice that we have x squared and minus x squared, which means we can cancel these out. Now what we have is we have both terms in the numerator have an h in them, and the denominator is h itself. So what we might do is we might divide both the numerator and denominator by h to get the following. When we have this, it becomes evident as h approaches 0, we are left with just 2x, meaning that the derivative with respect to x of x squared is 2x. Now we can use this kind of process for many different kinds of functions, and that's what people have done over the many years. So we have some important results to remember. So one of them is when we have x raised to some power. An example we've just seen was x squared, right? But with this expression, you can have something like x to the 4. When you take its derivative, you get 4x cubed, and so on. You might also take a function like, for example, sine of x, and try to differentiate that. And you can use some trig rules to show that the derivative of that thing is cosine of x. Similarly, the derivative of cosine of x is minus sine of x. Now, with some of these other functions, the derivative is also part of the definition of some of the numbers that are included in some of these following expressions. For example, we are aware of the function e to the x, or the exponential function, where essentially e is defined to be this number where e to the x differentiated with respect to x gives that function itself, that is e to the x. Similarly, if we have a logarithm to base e, or the natural logarithm, the derivative of that thing is going to be 1 over x. It's also interesting to understand how do we deal with more complicated functions. For example, what happens if we have a few functions added together and we try to take that derivative of that sum? So we can define something like f of x is equal to f1 of x plus f2 of x. Then, using the same principles as before, we just plug that thing into the definition of a derivative. So in this example, what we might do is we might split this fraction into two, where one of the fractions has only f1 of x in it, and the other one only has f2 of x in it. Now what we might do is we might just separate these two into two separate limits. And then it becomes evident, if we remember the definition of a derivative, that each of these terms is just a derivative of the corresponding function. So we essentially have the derivative of f1 plus the derivative of f2. So just to spell it out, the derivative of a sum of functions is the sum of the derivatives of those functions, or this thing right here. Another interesting thing to look at is what happens when we multiply function by a constant. What happens when we scale a function? If we have something like this, where f of x is defined to be c times f1 of x, we can check this again. If we plug everything in, we find that both terms in the numerator of the fraction have a c in it, meaning that we can factor that out like this, and then we can also bring that c in front of the limit, because c does not depend on h. We find that the thing to the right of c is just the derivative of f1 of x, meaning that we can write this whole thing in the following way. We can bring c in front of the derivative. So, the derivative of a scaled function is the scaled derivative of that function. And we describe this mathematically in the following way. Now, why do we care about this? If we combine these two previous results, that is what happens when we add functions and what happens when we scale functions, when we combine these together, we can show the following: that when we differentiate a linear combination of two functions, this can be expressed as a linear combination of the derivatives of these functions. More generally, if we take any number of functions and we add them together, each with a scaled factor, so we have a derivative of a linear combination of a number of functions, we can express that as a linear combination of the derivatives of those functions. And this makes d over dx a linear operator. In mathematics, this means that if we have some operator and we apply that to a linear combination of functions, if that thing can be expressed as a linear combination of that operator being applied to individual functions, we call that operator linear. And why is that important? Let's have a look. It essentially means that if we have very complicated derivatives, they can typically be decomposed into simpler ones. For example, if we have a derivative of x squared plus 5 sine of x plus 4x cubed, we can rewrite this as the derivative of x squared plus 5 times the derivative of sine of x plus 4 times the derivative of x cubed. And using the results before, we know what the derivatives of those simpler functions really are, so we can substitute those in. And then we have 2x plus 5 cosine of x plus 4 times 3x squared. And then finally we can simplify some things to get 2x plus 5 cosine of x plus 12x squared. So to summarize, we have the definition of a derivative, which is this limit as h approaches 0. Then we found that we can use this expression to find many of the derivatives of common functions. And we found out that d over dx is a linear operator